Everyone, it's December 24th. All right, so yesterday we were talking about despair, and things did start to look a bit brighter. The thing that got me really, really despair last night, it we're kind of having a hope, right? Kind of having a hope, but the things is still not 100% yet. So we will have to see if the thing can really be as good as it looks like at the moment. But anyway, we're gonna do this. Okay, it's an easy problem, so we'll deal with it very fast. What I just realized is I opened these two problems, right? I did not really know that this is a hard question as well. So either we have a competition, contest with two hard questions. Look at this, two hard questions, or man, it'd be fun. So we're gonna do this one, and we'll see if we can handle this. All right, anyway, let's look at this. Longest subsequence with limited sum. You're given an integer nums of length n and an integer query of length m. Return an array answer of length m where answer I is the maximum size of the subsequence that you can take from num such that the sum is less than or equal to this query. All right. So basically what we need to do is sort this and prefix sum, and then we can binary search. This will be 2. This will be 1 plus 3, 3 plus 4 will be 7, and this is everything. Yeah, sort them and then binary search. I think it's not the first time that we saw when we are dealing with subsequence problem, right? Because subsequence means the order doesn't really matter in this type of thing. The order doesn't matter, so we can always just sort it, and then we can return. Can we directly do that? I think we can. We just need to do bisect. Ooh, bisect what? Bisect right. So I think what we can do is for a q in query, all right, and then we're gonna just do bisect right nums and then q. I think that shall do. Give this a shot. Ooh, we got issue. Oh, Lord, I forgot. It should be accumulate. Accumulate sorted nums. Forgot to do this. My bad. No, that's the array. Oh, my bad. Accumulate, I have to turn that into a list. There we go. This should be right. That's it. Two, 3, 8, 9. Prefix sum of sorted nums, then binary search. Yep. On log n is this. Then it's on, and then it's om log n. So it's m plus n log m plus n log. All right. Oh, jeez. I didn't copy the. What's the solution? Sort and count. prefix sum of binary such. All right, so we're done with this. All right, let's try this. Add edge to, what's graph? Graph is always hard. Some graph is hard. There is a undirected graph. Add edges to make degrees of all nodes even. Consisting of n nodes from 1 to n. You're given the integer n and a 2D array of edges. So we have the edges. We can add at most 2 additional edges, possibly none, to this graph so that there are no repeated edges and no self loops. Return true if it is possible to make the edges of each node in the graph even. Otherwise, return false. The degree of an edge is the number of a node is the number of edges connected. So in this case, that's even, that's even, that's odd, that's odd, that's even. So 4 and 5 are odd, so we put 1 between them. That is possible. Ooh, it's not necessarily connected. So both of them, they're all odd. So are you telling me can we do this one too? So 1, 4, and 2, 3? That's also possible. Here, so 1, I need to create another edge with somebody, but I have no other people, no other nodes to create an edge with. I mean, 2 I can create, 3 I can also, 2 create, 2 and 3, that's good. But then 1 and 4 is still bad. But 1 and 4 is already connected. What do you think? I mean, what we can do, we can definitely count the number of edges, right? Once we count the number of edges, can we say that if 2 nodes, if they both have odd number of edges, then we can always, if they are not connected, then we can connect them, and then they each add a new edge and it's independent of everybody else. Then it satisfies the requirement. If both has odd edges and they already have an edge between them, now that case will be a little bit difficult to deal with. We can try. Yeah, we count everything and then let's leave all the even edges alone. And we'll look at all the odd edges. Okay, so we have a list of odd edges. And what we need to do is to find among this list which pair does not have an edge already. How do you find that? Well, if I have an edge, or I have a node, right, and I know its edges, and I need to search for, damn. So we have to search, right? But I don't think this problem is that easy though. What I'm saying is we have that, right? And then we have a odd edge 1. I mean, we can odd edge. Oh, I can have a list, right? I have a list. I don't know. Yeah, I have a list of things. I have a list of nodes. Okay. They all have odd number of edges. And then if I take the first one, I know what it is connected to. And the question is, how do I find among the remaining which one is not in there? I mean, we can just search. We can search it one by one and find the first one that's not in it. We can also put it as a set. The first one's not in it, then these two will be gone. Right? These two will be gone. I can basically delete these two. Then we go to the next one and we search again. And eventually, if we hit one, then we search through everything, and then I want to give it a shot. There's a very high possibility that this is not going to be right. But what do I have to lose, right? I don't think there's anything to lose. Okay. And we can only have two. Another thing we can do is, so we say odd nodes, right, so equal to for kv in graph dot items if len v is this, and then we will do k. I just want to know the nodes. Okay, and then they need to pair, right? So if they need to pair, because that's the best way we can do, then we can say if k is this, then we can return false. Because if I have odd number of nodes that need to do, then we pair one, we cannot pair another one, right? It's impossible to pair the other one. So we say if it's this, then we cannot do. And if we do pair, then just we say if k divided by 2 is larger than 2, because we say we can only add 2 edges, which means it can only be 4 nodes. Yeah, we can actually just say, well, it's k. No, it's len odd nodes. We can also say len odd nodes is larger than 4, or this. Yeah, if I have too many, then it's not going to work. So now we only have, wait, did it say 2? At most 2 additional edges. Yeah, then we only have 4. Then we can just check to see if we can make it. Really? Huh. Really? I don't think this is right. I feel like I'm stepping into a landmine. Then what you do? Then I basically have 4 and I just try. Right? I'll take the first one and take the second one. And then go to the second one and then see if it works. You can say for I in range. But in this case, I can actually put. Right? And then all of this. M, so it could be in range M, with J in range I plus 1 to M, right? We say if odd nodes I just feel weird. Right, I just feel weird because we only have 4 or even fewer. 4 or 2. That's the only 2 possibilities. Right? We actually say if M is 0, right? So if M is 0, just return 0. Otherwise, if M is 0, then we'll return true. If M is equal to 2, we'll return R node 1 not in R node 0 graph R node 0. Okay, now if we have 4, then we have to choose. When we say for J in range 1 to M, right? How do we do this? We want to find one. Yeah, because it was 0 and then we try to find one. So we say if odd nodes J is not in. Oh, we might have different choices. Okay, but for choose 2, I think that's actually might be a better choice. For choose 2. How do we handle this? Just 0, 1, 0, 2, 0, 3. So 0, 1, 0, 2, 0, 3. Yeah, so it's just four situations, right? Yeah, if M is equal to 4, we should return 1 not in graph 0 and actually no, any, okay, any one of these. If it's true, then it's true. So this is not in this, and so 1, 0, and then 3 not in 2, right? That's the first situation. Second situation, 2 not, so 0, 2, and a 1, 3. All right, third situation is 0, 3 and 1, 2. Something like that. I'm not sure. This looks very shaky. I mean, I think I can pass these test cases, but it just feels not right. It does not feel right at all. Feels forced. You know what? I'm actually very curious. I want to know, like for real, I want to know what test case there will be that make this wrong. Jesus, possible. All right, show me an error. You show me an error, I'll be happy. Okay, got an error. That's what I want. But Lord, oh my God. Oh my God. Oh, just this passed so many already. Okay, though that's why it's a tough one. Yeah, but how? Right? How? How? Output false, but actually true. All right, so now what we need to do is make it simpler. I can. It's a 21. That's too much. I don't know. I mean, what are we gonna do? Just delete some? You can't just delete some. I mean, if you delete some, I might. Lord. I just delete some and try to see if it works. Ah, Lord, it works. I really have. Oh my God, it works again. That is too bad. That is too bad. All right, so basically it just says there's no other way except we try to do it. Man. All right. There's no other way. There's no other way. So it's supposed to be true, but I say it's false. Okay. Let's see. 2, 3. Two and 3. Okay, so we will do 2 and we will do 3. Let's see. Oh my God, they connect to the exactly same nodes. So 2 connects to 3 and connects to 4, 5, 6, 7, 8, 9, 10, 11, 12. Every single one. Oh my God. Connect to every single one. 3 connect to every single one as well. And we have 19. To 1. Who is 1 connected to? Who is 1 connected to? Oh, I see. Holy crap. That is a way. That is a way. Oh. So what do you say? Yep, we can connect to another one. And we can get both connects to another one. And it will only be used if there are... Holy crap. How am I gonna do this? All right, so basically, m equals to 2, we have another situation. M equals 4. Dude, m equals 4. If we find 2, and we find another 2... Oh, man, is there a better way to do this? No, if m equals 4, right? The only way, because we can only allow 2, so if m is equal to 4, that is the way. If there's something wrong, then there's something wrong. It's only m equals 2. So we'll say, we say if this is true, then we just return true because they can do it. If it's not true, then we'll have both stick out, right? And it has to stick out to the same thing, which means we're going to find a node that doesn't exist in either one of them, right? And how do we do that? Well, we can do that by union their neighbors and then to see which one is not in. Okay? So basically we're saying for node in range 1 to n plus 1, okay? If node is not equal to odd nodes 0 and node is not equal to odd nodes 1, we can just say if node is not in odd nodes, all right, so it's not these two, and not in odd nodes this, so we can do, yeah, that's fine, not in this and not in this. If we have a node, then we will return true. Otherwise, we'll return false. What the hell? Okay, you want to give this a shot, buddy? Yeah, I think, I don't know, this looks like it might work. Try again. Huh, it worked. I mean, in the actual contest, it will be difficult because I will not realize that there's another way, but now that I see it, it's okay. All right, it's okay. Huh. Very interesting. Yeah, I mean, this is a cheat, okay? A little bit cheating happening here. All right, since I can, okay, so first of all, to use the least number of additional edges, we want the odd degree nodes to pair with themselves. cells. Okay. So we build the graph and take out all the odd degree nodes, right? Now, if the number of odd degree nodes is odd, right? That means, hold on. If the number of odd degree nodes is more than 4, right? We have to use, we cannot use just 2 additional edges. So also, if the number of odd degree nodes is odd, right, that means we will always leave one node with no pairing. That is also impossible. Thus, we narrow down the search for 2 or 4 odd degree nodes. Now, when the number of odd degree nodes is 4, right, we must pair them, right? We must pair them, and it's not difficult to do, not terribly difficult to do. Well, not then, it's when. If the number of odd degree nodes is 2, we can pair them, or if they cannot be paired, we can also pair them with a third node, right? With a third node, such that each of the odd degree nodes receives 1 edge, and the third node receives 2 edges, maintaining its even degree status. Now, the last situation of using an additional node, I did not come up with it. It was from trial and error, so it counted as cheating. But anyway, solve it. That would be that's just ON. Well, ON plus, no, it's just ON plus, ON plus M, right? Where M is the size of edges. Okay, so I need to see. Yep. 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 Okay, so this one is fine. Nothing actually to, what's the hints here? I think we got lucky. Like initially we were on the right path. That's what I think. And this could have been done nicely. Looks quite bad. All right, anyway, so let's move on. We have some time. I can do the last one. Cycle length queries in the tree. you're given an integer n, there is a complete binary tree. What's a complete binary tree? Is it to fill everything, or actually I don't know. What's a complete binary tree? I suppose to know this. All the levels are completely filled, except possible the lowest one, which is filled to the left. Okay. So what's the one that's... Oh, it's a full binary tree. Gotcha. So that's the difference. So complete doesn't mean it's full. We have n, hold on, 2n minus 1 nodes. Wait, 2n minus 1 nodes. That means it's full, right? If it's 2n minus 1 nodes and it's a complete binary tree, that means it's a full binary tree, because you do 1 plus 2 plus 4, right? That's 7. Next one is 8. That's 15. So yeah, it's always going to be full. I think it's a full binary tree. Root is 1, and every node in the value in the range of this and this. That is correct, right? That is correct. It's n minus 1 minus 1. Hold on. Oh, yes, this one has 2 children. Yes. The left is... That is correct. That is correct. You're also given a 2D integer array, queries, of length m, where queries I. For each query, solve the following problem. Add an edge between the nodes. Find the length of the cycle in the graph. Remove the added edge. A cycle is a path that starts and ends on the same node, and each edge in the path is valid only once. The length of it is the number of edges. There could be multiple edges between 2 nodes in the tree. There could be multiple edges. Yeah, if we do this, now we have then 2 nodes in the tree after adding the edge. Then we just say be 2, right? Okay, so 5, 3. So I have 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3. Oh my god, this is a very... yeah, I was talking about this. Wow. This is a very interesting problem. Okay, it's a full binary tree. And we just add an edge. Yeah, any edge we add will create a cycle. It does not matter. Any edge we add, because it's a full, everybody's connected to everybody else. So what we need to know is just the height, right? The height of one node, the height of the other node, and add 1. And how do we know the height? By doing this. We can know the height by, I think some log operation will know the height already. Like this is 1. We can just say log this, the height is 0, right? 2, if we log this, the height is 1. This log it, the height will be 2. So if I do log 5 plus log 3, integer it, log 5 plus log 3, and then plus 1. Integer it. Let's do floor. Floor it, and then plus 1. And this is... And if it's this... What do we do if it's this? Well, if it's this, if I log this, that will be 0. I log this, that will be 1. Right? So it will be 0 plus 1 plus 1. Really? That's it? Huh, that's it? Let's say for Q inquiries. No, Q is only two things, right? So A, B inquiries. We're gonna say math.log. Hold on, I'll have it be log2. Oh, math.log2. A. Right, we can say math.floor plus math.floor B plus 1. And we'll return this. Something is not right. Again, I don't know. Something doesn't feel right to me. Man, this feels sounds very shaky. Sketchy. That's the word I was looking for. It does pass. I can do a check. Let's say, I don't know, n equals 20, right? And then, yeah, I can do a check. Yeah, let me do a check. Not confident. Right, and say for this in range 100 test cases, what do we do? So we need rand int 2 to 30, right? And then we need queries. And say and say, so these two can be, as long as they're not the same. As long as they're not the same. So queries equals this. Okay. So this in range, I don't know, we can do let's 100. Yeah, let's do 10. Yeah, let's do 100. That's fine. Okay. Then a equals rand int, right? 1 to 2 to the, oh, we have to say n. Okay, so this will be 2 to the n. I don't need this. 2 to the n minus 1, right? And then we say b equals rand int 1 to 2 to the n minus 1. Say while b is equal to a, b equal to rand int 1 2 to the n minus 1. All right, and then come out, I'll say queries AB, and I'll print queries. Now select these. Oh Lord, too many. And give it a shot. Oh, it's not right. That's not right. Wait, hold on. Okay. Let's see. That was wrong on so many levels. Oh, I don't know what I was doing. I see what the problem is. Dude, come on. You gotta be smarter. I need to find their common ancestor first. Sorry. Very sorry. I forgot their common ancestor. Okay, so we're given the two, we need to find their common ancestor. Because that's where the cycle starts. Alright? So now the question is, how do we find the common ancestor? Yeah, like if we connect these two, their common ancestor is 3, so that's the cycle. The common ancestor is found by, I've done this before, common ancestor. Common ancestor, 2 nodes common ancestor. Two nodes, common ancestor. Dude, I forgot. Hold on. I remember. So we start from here, right? And then we say this, and then this is common ancestor. And then we basically said, hold on. I know. I know how to do this. Once I get to the node, right? Then the common ancestor is this. So I return my common ancestor, right? So for each thing, I have a left and I have a right. And then on the left, on whichever, if I find this a common, if no, I can just return to -1, right? Or return 0. And if I find it, I'll return that common ancestor. So if at a node, right, and on the left, I'll return something, on the right I'll return the first one that have both the left and right, return the target. That will be the common ancestor. So we will find the common ancestor first. So def common ancestor. Okay. Common ancestor, what do? We will have a node and we'll return, should be the first one, right? Should be the first one. And if on one side we have, and then the other side we don't have, should be the first one, so like each one of them doesn't have, like we need to check if it's found, right? It's found. If it's found, then we just return yeah, basically we say if the left and right, yeah, it has to be from left and right, the common ancestor. That doesn't mean no. What it means is if outside my current step I have both of them. I remember this is a if it exists. Yeah, so we have two nodes, right? If it exists, so queries, right? We have A and B. So if it exists, we're gonna return 1 0 or 0 0. 0 0 doesn't exist. 0 1 1 doesn't exist. 1 1. So the first one we get is 1 1, right? Then that's the thing. Okay, so okay. Whew. So we're gonna say 2 times this plus 1, right? And then when we add it at the end, we'll have a total number. The largest is 2 to the n minus 1, right? So I'm gonna say n is 2 to the n minus 1, right? We just say if node is larger than n, right? If node is larger than n, return 0. Otherwise, we can say left right equals common ancestor 2 times node, that's left, common ancestor 2 times node plus 1, right? And then current A and B, my bad, it should be A and B, that's the two things, right? So we're gonna have to pass down A and B. AB, AB. Okay. And we say C will equal if node is equal to A, then C equals 1 0, which is 2. Okay. I'll kind of do this one. If node is equal to B, then C equals 1, else C will equal to 0. Yeah, I'll do it fast. C equals to 2 if this, else 1 if node equal to B, else 0. And now we put this in the parentheses. Okay, so that's C. And we say if L or R or C is equal to 3. Right, 1 is 3. And self dot and not self dot ca. Self dot ca are equal to node. And now we return L this R this C. So if node is larger than n, return 0. Okay. We can also say if I already found it, right? We say if not, if self dot ca, then we'll just return. So if self dot ca or we should return 0. I don't really care. Actually, no. If I want to be at absolute correct, if this, we shall return 3. So we need to call common ancestor starting from 1. Okay. Oh, maybe that's how we get things more complicated. Hold on. So now we have to do this way. For AB in queries, Holy crap. We'll do A1, AB, right? We'll find this common ancestor. And then res.append something. Master floor A, and then we need to minus the height of the, so we're doing this plus this, so this minus, we might actually just do HA, HB, and HCA, common ancestor, equals this, and this, self.ca, right? So we do this, and then we're gonna append HA minus HCA plus HB minus HCA plus 1, right? Once we're done, self.ca return back to 0, and we'll return res. Okay, we try this, still pass. Go here, try the remaining. Why is this one? Okay, run it. Looks good. And we're going to use, well, have all of them. Some. Okay, try this. See how it goes. No. 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 Oh, you want to try? Yeah, I want to try. We're in a timeout. I know it's gonna time out, but yeah, I'd like to put a timeout there so we know that this is the first attempt. Okay, so it's the right way. So, but we just have to be smarter when we calculate the common ancestor. I mean, what we can do. Let me see how many we do. Only 13 out of 27. All right, so the answer is correct. It just took too long. So basically, I mean, we know the path, right? Every single one, we know the path. And then given, so basically we want to say, if I know it's a full binary tree, and given any two nodes, what would be the fastest way to know what is its common ancestor? I mean, we can basically, we actually don't need to traverse. We can just divide by 2. Divide by 2, divide by 2, divide by 2. And we'll find yeah, so we don't have to do this. Common ancestor, right? So we just, so we can say, hold on, we can say CA. CA equals this, A and B, right? We just need to find a common ancestor. What do? We don't even need this. We just need to say ancestor A ancestors A equals ancestor B equals a set and a set. Right, so while A, I put A in there, put B in there. While A says A dot add A divided equal to 2. And now we just add this. I want to do the same thing. And then we use a DP. Right? What is DP? DP, I mean, the easiest way is going to be just a dictionary. Right? Just dictionary. And now we say if A not in DP, then we say DPA is equal to a set with A. Okay? And then while DPA dot add A. And then blah 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 blah. The last is 1. Oh, we'll add 0 to it. Wow, A is larger than 0. Well, A is larger than 0. Yeah, well, A is larger than 0. So when it's 1 going up, and then it becomes 0. I want to add it first and then do it. You know what? Yep, I need to add it before I do it. So this is going to be a set. And now I'll add A. Oh, I cannot use A again. Dude, that's not fun. Temp equals A. Okay. So while temp, we will do temp. And then temp will divide equal to 2. Right? And then 1 and then 0 will jump out. So that's that. If it's not in, that is what handle B. Right? If B is exactly the same. Right? So we handle A and B. And then we just need to say intersect. Oh, intersect. And we don't need to have intersect. I just need the smallest. No. It's not intersect. So this is the path, right? So we have the path and we have another path. So what I want to know is the first one that was the last one, they're the same. Which means if we go from the start, now we kind of go, and the first one we meet, the first one, the biggest value, they're still the same between the two. So we can do intersect. We can do intersect. We can do intersect and take the largest value. So we can say return dpa dot dpp. Actually, I'm not sure. Is the intersect work? A dot intersection. Okay, so I have to say A dot intersection, and then be the maximum of this. So with this, CA equals this. Let's give this a shot. Do we still time out? Nope. Ew. Wow, this is a pretty easy contest. So, a complete binary tree with how many nodes? 2 to the n, right? 2 to the n minus 1. With 2 to the n minus 1 nodes is a full binary tree. Actually, this doesn't really matter, okay? Yeah, it doesn't really matter, even if it's not like that. So yeah, so we're gonna say given the 2 nodes, right, in query, we need to find their latest common ancestor, earliest common ancestor. What is it called? Most recent common ancestor. Wait, what's the word? Common ancestor. Tree. Most recent common ancestor. I'm not sure. I don't think that's the one. It is most recent common ancestor. I find their most recent common ancestor. Right? And the cycle length size, right, is the height from the most recent common ancestor to one node plus the height from the most recent common ancestor to the other node plus 1. Now, since we are given a complete binary tree, we can use we can divide each node by 2 to find all the nodes on its path. Thus, finding 2 nodes most recent common ancestor is equivalent to find the largest value, largest node in their paths that shared, right, in their path. We can achieve that by using set to represent the path and find the max of the intersection of the set. The height of a node can be computed as a math.floor math.log2 node. And overall will be O query. Let's call the query size is M, right? And each time we're going to do this is basically log n. And no, don't count these. Okay, let's see. What are the solutions? Lowest common ancestor. Oh, they call it lowest common ancestor. Look at this. Minimum x and y and the maximum. Oh my god. Oh my god. Oh my god. Oh my god. Holy crap. All right, I'm speechless. Yes, that's the way to find a common ancestor of two nodes in a complete binary tree. Lowest common ancestor of two nodes in a complete binary tree. Brilliant. So res equals this. For I use AB in queries. Res dot append -1, not -1, not append 1, and then while a is not equal to b, wait, hold on. We add this, and then we go, that's 1, right? And then wait, hold on. Because they both go up, right? Shouldn't that be counted twice? But he only counted once. Number of steps on one side and the number of steps on the other side. Oh, because each time only one of them goes up. So the, oh my god, this is so good. This is so good. Now this is brilliant. Each time we keep the smaller of the two nodes and get the parent of the larger node. Notice that by doing this, even doing this, if the two nodes are on the same level, it is guaranteed that one will get elevated earlier than the other, which means we are able to count the height, right? Count the step of both. We're able to count the step of both, which means the one that goes up earlier always waits for the other one. That's the thing, right? And then we just say res -1 plus equal 1. Return res. Holy guacamole! This is brilliant on a whole nother level. Can't even like express myself. This is so good. I mean, it's the same, but it's so much better. Again, I call it OM log n. All right. Now, these are not difficult questions. Either I'm on fire today, or I just these are not right. They significantly reduce the difficulty. Like the earlier difficult questions are real difficult. This is like all right. Okay, that'll be it. We did pretty well today, huh? 1 hour 60 minutes. We got 3 done. I will see you guys tomorrow. Adios.